Good afternoon. Welcome everyone to our Ertl lecture. It's a pleasure for me to introduce the Fritz-Haber-Institut. I'm the managing director, Beatriz Roldán, and I'm very excited about having our awardee today, Professor Graham Hutchings from Cardiff University. I know Graham Hutchings, we were talking yesterday, probably over 24 years. And he's a pioneer in the area of catalysis, of heterogeneous catalysis. And he has been a mentor to many very well-known researchers in the field. So he has not only produced excellent science, but also been an excellent producer of minds. So we are going to have a very exciting evening with science, with some interactions with people from the different Berlin universities. The Ertl Award is funded by BASF and is through a selection that involves all the directors of the Fritz-Haber-Institut and also the local universities. We have here presidents also from the local universities, Humboldt-Universität Berlin, also FU Berlin and TU Berlin. I want to also thank everybody that is here for coming to our Ertl lecture. We have Gerhard Ertl, who is going to be online listening to the lecture. We just met him today for lunch, and we had a very nice scientific discussion. And I'm sure that after the talk, he will have also some words. So thank you, everybody, for being here. And I will move on to the president of the Humboldt-Universität Berlin, who is going to say also a few words, and then we will go into the Laudatio.
Dear Professor Roldán, thank you for your nice introduction. Dear colleague and award winner, Professor Hutchings, dear Professor Ertl, dear Dr. Kratz, dear colleagues, dear guests, ladies and gentlemen. It is my great pleasure to welcome you to the 2024 Gerhard Ertl Award Lecture. As the president of Humboldt-Universität zu Berlin, I'm honored to extend my greetings on behalf of our partner universities, Freie Universität Berlin and Technische Universität Berlin. The close collaboration among Berlin's 3 leading universities plays a vital role in making this event possible, underscoring the importance of cooperation in the scientific community. The Gerhard Ertl Award was established in 2008, so it's actually 10 years older than the Berlin University Alliance. And it proves that collaboration between Berlin's universities and Berlin's very strong non-universitarian research institutes has a long tradition. This award is the result of a long-standing collaboration between Berlin's major universities and the Fritz-Haber-Institut of the Max-Planck Society, a partnership we can trace back to the institute's founding in 1911. Today, and we also, of course, owe a great thank you to BASF as a long-standing partner who make this award possible. Today, close collaboration between Berlin's leading science and research institutions is more important than ever. We in Berlin, as most other Länder in Germany, are facing significant cuts in state funding for higher education and research. With our spirit of cooperation in the Berlin University Alliance, in which the 3 universities in Charité Universitätsmedizin work together very closely, and in the integrated research area Berlin, with our close partnerships with strong societies as Max Planck, I think that we are prepared for times of crisis. We are better prepared than many other regions, because jointly we can and we should spread the message that universities and research institutions are crucial for Berlin, for its innovative spirit, the education of our future leaders, for the provision of skilled labor, and for facing the great challenges of our times. And jointly, we can develop the integrated research space even further, even in times of shrinking budgets, because we know our strength. We can create synergies and shape our profile together. it is important that we convene here today to send a signal of the strength of science, not only, but also here in Berlin. The Gerhard Ertl Award honors researchers who have made groundbreaking contributions to the field of catalysis, a domain profoundly shaped by its namesake Gerhard Ertl, Nobel Laureate in chemistry and former director of the Fritz-Haber-Institut. And we are privileged to have Professor Ertl joining us today via Zoom. With the support of BASF, the award not only recognizes exceptional achievements, but also promotes the exchange of innovative ideas and catalysis research. Our awardee today, Professor Graham Hutchings, Regius Professor of Chemistry at Cardiff University, exemplifies the values this award seeks to uphold. His distinguished career from his early days at ICI Petrochemicals to his current role as Regius Professor of Chemistry is marked by extraordinary scientific breakthroughs and numerous accolades, including his election as a Fellow of the Royal Society. Professor Hutchings, your pioneering work and exceptional contributions to the field of heterogeneous catalysis reflect your unwavering dedication to advancing the frontiers of science. And I'm very much looking forward to your lecture, and I hope that even as a political scientist, I will be able to get an idea of how innovative and important your contribution to this field of research is. So, welcome again to today's award lecture. I wish us all an enriching and inspiring evening. Thank you.
Yeah, good to be back here. And as BASF, I'm really happy to give the Laudatio again to an outstanding awardee, I must say. So, dear Julia, dear Beatriz, dear Professor Ertl online, dear Graham, ladies and gentlemen, what a great pleasure and honor it is for me to introduce this year's winner of the award, the Gerhard Ertl Lecture Award. The committee has chosen Graham Hutchings for his groundbreaking contributions on gold nanocrystals and gold palladium alloy catalysts that have revolutionized the selective oxidation under mild conditions. Gold. What a wonderful element. Why do we love gold so much? Why is a golden medal such a big aspiration? Why are people happy to invest into gold, and why are gold prices so high? So I bought a sheet. This is the gold price. And the question is, maybe this has something to do with Graham and his research? So let's see. Before I try to answer this question, I want to repeat a little bit what Julia said and dive deeper into the accomplishments of our awardee later, but let me say a few words about the award. It was in 2008, as already mentioned, that the Gerhard Ertl Lecture Award was established and presented for the first time by several renowned institutions, 3 Berlin universities, the Fritz-Haber-Institut, UNICAT, and BASF. And the intention was to express deepest appreciation for one of the most prominent scientists in the field of catalysis, who was awarded the Nobel Prize in 2007. This is you, dear Professor Ertl, online at the moment. Well, this prize tonight is awarded for the 17th time. It is highly regarded in the scientific world, so to speak, the gold standard in awards related to catalysis. And the impressive list of previous award winners shows this very clearly. It also underscores our winning, if not golden partnership between academia and industry. And here in this audience, I don't have to emphasize the role of catalysis in terms of importance in chemical processes. But I think everybody knows this, and let me just add that for BASF, catalysis has played a crucial role ever since we developed the ammonia synthesis and its catalyst in cooperation at that time with the University of Karlsruhe. And that was over 100 years ago. And throughout the history of our company, collaboration with academic partners has always contributed significantly to our research, but also to our business. And we have remained true to this spirit of cooperation, and that is why we founded BASCAT at the TU Berlin in 2011. BASCAT is a laboratory jointly operated by UNICAT and BASF with focus on new catalytic processes that contribute to the search for alternatives to fossil feedstocks, and really important and groundbreaking moves that are developed there. But back to the present and the most important topic of tonight, let me introduce this year's awardee in more detail. I would like to do this and approach this using the word gold, as in G-O-L-D. And let's start with a G. G, not for Graham, that's too easy, but rather as in groundwork. And in Graham's case, it's somehow been quite unconventional groundwork that has led to an outstanding scientific career. Graham has taken a distinctly different path compared to the typical academic profile. That is, you first complete your PhD, then postdoctoral research, then followed with tenure track and future research, but all in the same field. With Graham, things were different. So let's start from the beginning in the 1970s, when gold was priced at a mere $100 per troy ounce. Graham studied chemistry at University College in London then, and gained his Bachelor of Science in Chemistry in 1972 with first-class honors. Following a PhD in biological chemistry on in vivo ATP synthesis in 1975, he joined ICI. In fact, he was hired for a biological chemistry project, but as industry has it, ICI scrapped the research before Graham even joined the company. So he was forced to switch fields to remain with ICI, and this is how heterogeneous catalysis came into play. A good move, as it turns out. He was with ICI 9 years and worked in research and production-related positions, first in the UK and then from 1981 onwards in South Africa. His actual academic career started in 1984, when he joined the Department of Chemistry at the University of Witwatersrand in South Africa. And here, he established himself as an internationally leading researcher in heterogeneous catalysis. By then, gold prices had climbed to $500 US. In 1987, Graham left South Africa and joined the Leverhulme Center of Innovative Catalysis at Liverpool University, first as assistant director and later as deputy director and professor. This move was somehow accelerated by the so-called tomato affair. Story has it that his wife Sally hurled 2 tomatoes at President Botha during a cocktail party. You can say if this is true, but the story made it actually to the Los Angeles Times. Unfortunately, gold prices dropped back to 300 then. But in 1997, he moved to the University of Cardiff to become head of school and professor of physical chemistry and pursued new research approaches in catalysis research. In 2008, he founded the Cardiff Catalysis Institute, which is now one of the most renowned catalysis research institutes in the world. And in 2016, he was the first professor to be appointed as Regius Professor of Chemistry, a position awarded to the University of Cardiff due to the reputation of exactly this institute. Gold prices had gone beyond $1,000 US by then. The next letter in gold is the O. This clearly stands for your outstanding scientific creative power and the incredible number of honors and awards you have received. I will mention only some that you have received during the last 15 years, because naming them all would go far beyond my speaking time. You are a Fellow of the Royal Society and an elected member of the Academia Europaea. You received the Alvin Mittasch Award from DECIMA and the ENI Award in the category of Advanced Environmental Solutions. You received the Royal Society of Chemistry Faraday Lectureship Prize, and you were appointed Commander of the Order of the British Empire, CBE. And since 2023, you are a Fellow of the Royal Academy of Engineering. During these 15 years, gold prices have climbed steadily and have meanwhile topped $2,000 US per troy ounce. And now, with gold at an all-time high of currently over $2,600 US, we are more than delighted to add the Gerhard Ertl Lecture Award to this incredible list tonight. Let's continue with the L in gold. and your love for science. Your work covers an immense range of topics, encompassing numerous areas of catalysis with several pioneering approaches. And these include novel methods of catalyst preparation for both metal oxides and supported nanoparticles, selective oxidation, acetylene hydrochlorination, and direct hydrogen peroxide synthesis. Your main research focus are gold-based catalysts, and your contribution to discovery, understanding, and application cannot be valued highly enough. And speaking of application, a gold catalyst based on one of your discoveries has been commercialized in China by Johnson Matthey, thereby substituting the use of mercury. Your publication list is outstanding, and it covers an enormous range of topics. Overall, your track record encompasses almost 1,000 publications and more than 58,000 citations. But it's not all about numbers, as impressive as they are. I think even more important is that you are a great mentor to many, helping numerous students to launch their careers in academia, in industry, and in a wide range of other professions. Your enthusiasm and your creativity are widely valued, but what most underscores your love for science is the capability to think across disciplines, or even outside disciplines. The combination of providing a lot of good times and fun together while engaging interesting science has created such an amazing output from your research. And now to the fourth letter in gold, the D. D like diversity. It would be hard to find a scientist with a broader and more diverse background of interests. You have reshaped your research, engaged in new fields several times, and have a proven track record in opening up new areas of heterogeneous catalysis using multidisciplinary approaches. Your focus was never only on academia or only on industry, which makes you the perfect interface for these two worlds. That's an important aspect because, in my mind, often these two worlds are too far apart. Your research activities are of high industrial relevance, and at BASF, we are very proud that your work has inspired a number of joint research projects as well. And your diverse interests go far beyond pure chemistry, but what they all have in common is that you tackle everything with full enthusiasm and passion. Where others only do a little bit of gardening, you dig deep, so to speak, digging for gold. And in this spirit, you fully engage in your hobbies. Consequently, you are very proud of your own farm and the fact that your family grows much of the food you consume yourselves. And similarly, just enjoying wine is not good enough for you. You are a member of a wine tasting club. I think it's online, but this also takes it to the next level. Looking at all your honors and awards, one could think you could only care for science, but the mentioned examples show that the opposite is true. And that is what makes you so remarkable and the outstanding personality we are honoring today. Dear Graham, I hope I could convey to you and the audience here how invaluable you are to the global scientific community, but also how important you are to everyone investing into the wonderful element called gold. And maybe also in science, Julia, it would be nice if people would be investing more to show that this should be the graph to show the investment into science and supporting universities. I truly believe this is what needs to be done for the future. My sincere congratulations on your lifetime achievements and today's Golden Award. And now, Graham, we are looking forward to your lecture, which is titled Catalysis Using, what else? Gold containing materials. So, thank you very much, and please join the stage.
Is this, oh, it's on now. Okay, thank you very much. Thank you for the kind words of introduction from both of you. It's a great honor to be here with you today, and amazing to hear my life story read out. Yes, the tomato incident is true. Okay, it wasn't at a cocktail party. It was at her university where he was being awarded a prize at a time when there was a lot of strife in the country. So it meant we left South Africa very rapidly anyway. So that was, there's some upsides to things. So it's a great honor to be here, and it was a pleasure to have lunch with Professor Ertl. He reminded me that the first time we met was in 1978 when I was in ICI. So we go back a long way in that sense. I think I'd like to mention initially that I then became really interested in Professor Ertl's work when I was a member of the Fachbereich here, when I started in 1999. And at that point, he was doing his groundbreaking work on oscillating reactions on surfaces. And I think that that still underpins a lot of scientific thinking today, and it shows the seminal work that he was able to do here at the Fritz. And so it's a pleasure to be here. I've long enjoyed visiting the Fritz. And so what I will talk about today, I hope, will live up to the comments that have been made already. And what I want to talk about is effectively three things, but it turns into 6 topics eventually. And I do want to talk about acetylene hydrochlorination at the start, because that's where I really started with gold. And then I want to go on to gold palladium catalyst. When somebody gets married in the United Kingdom, I don't know if it's true elsewhere, you say that the bride should always have something old, something borrowed, something new, and something blue. Now, I haven't got something blue, except occasionally there'll be some blue colour on the slides. But I will have something old, something new, and there'll be one thing that's borrowed in this presentation. And I hope to mention it when I see it. So, as I go through with the topics, I'm going to give the acknowledgements and the funders. So I'm not going to mention the funders there. They will be there in their logos. But the project team, in this case, involved 2 students, Grazia and Simon. Simon Freakley was a postdoc, and we had 2 excellent technicians that helped with the characterization, and Chris Kiley, who's a well-known microscopist to a number of people. I've worked with him, I was trying to work it out, since about 1989. So we've published a lot of papers together. And this one here, this is Peter Johnson. He's central to this story all the way through the acetylene. And he was my first PhD student in the University of Witwatersrand. So it's nice to see that, you know, that he's come back into it, so to speak, and we're still working together. And at the back here in my office, this is a picture of Crown Mines, which is where a lot of gold has come from over the last 100 or so years. So, and I'm drinking out of a gold ACS mug at that point. Okay, so gold features heavily as we go through this. So, my story with gold starts with this piece of work. I was asked when I was working with ANCI, I was seconded by ICI, to come up with a better catalyst for this reaction of acetylene hydrochlorination. Hang on, I'm pushing the wrong button as always. I shouldn't be giving these things. In every lecture I've given in the last year, I keep breaking them. So I hope you've got several supplies for these. So this reaction, a highly exothermic reaction, and it's currently very big production of acetylene hydrochlorination in China, around 18 million tons. It's probably growing above 20 million tons now. And the plants look like this. Each plant will have about 100 reactors in pairs. Each of these reactors contains 6 to 7 tons previously of mercuric chloride on carbon, 10% mercuric chloride on carbon. It's a hideous catalyst. And under the reaction conditions, the mercury is lost, it gets reduced, it comes out as metallic mercury, also methyl mercury. There's lots of nasty compounds that can be formed. And each year around 1,000 tons of mercury is being lost to the environment. And that's an environmental disaster. It's a teratogen at parts per billion. So tons is a really dangerous thing. And I was asked to come up with I don't know what I've done to that, a better catalyst for this reaction. And I found some data in a paper, and I just replotted that data. So I never did an experiment. I just took the data in this paper and I replotted it. And I replotted it as the conversion that was been in the paper, but the person had plotted it against the electron affinity. And I thought, no, let's plot it against the standard electrode potential. And when I got that data, I looked at this and I thought, if that's right, gold will be the best catalyst for this reaction. Now, I've been told by a number of electrochemists that you should never plot kinetic data versus dynamic data. And I just say, well, it doesn't matter, it works. This correlation is true. When you do the experiment, here's mercury, here's palladium, platinum, iridium. You'd never use iridium for this guy. At least you shouldn't. And here's gold. Gold is the most active and the most stable catalyst for this reaction. Now, there's lots of literature on this now. There's hundreds. There's thousands of patents on this reaction. There's more patents than there are academic papers. And it's probably because this is not an easy reaction to use, to work on. It's where you've got high temperature HCl, and your reactor is basically a disposable item. You go through the reactors on a regular basis. So it's also, you need a lot of money if you want to do this chemistry. But I'm a poor academic, so if there's anybody in the audience who wishes to sponsor this, please do. All those papers, if you read them, they say they have the best catalysts for this reaction, platinum, palladium. And what they do is they test it under ideal conditions for their own reaction, and then they show that other catalysts aren't quite as good under those conditions. But when you actually compare everything, and we published this in Nature Chemistry Reviews a couple of years ago, it's quite clear that gold is the best catalyst for this reaction when they're compared on an equal basis. So luck played a really big role in this. The first is I was lucky to work on this. I was in industry, and I was told by my boss that we had to go to the production units and teach them how to make their product better. And I said, this is ridiculous. I had been a production manager myself. No production manager values a research person coming and tell them how to run their plant. I think if I've got industry people there, I think it's clear, okay? I said, they will laugh at us. And he said, no, you're coming, and that's it. I said, no, I don't want to go. Anyway, a direct order in industry, you have to take it. So I went, and they didn't quite laugh at us, but they didn't treat us very kindly. But in the end, they gave us this problem to work on. So it was lucky that I listened to my boss and I went and did this problem. The other is that you'll see that I published the correlation in 1985. I followed this up with, this was published in 1996, but the first paper showing this was in 1987. But I did the work in 1982. And so I was lucky that I was able to publish this, the correlation, because once I published this, I could do this. And it was luck because the company was trying to commercialize that catalyst, but the person who approved the publication didn't know that. This often happens. Companies are big, and lines of communication sometimes don't work. So I was very lucky. And the other is that we didn't have a soluble form of gold. Chloroauric acid would be the classic material to use. We didn't have it. We only had gold powder, so we dissolved it in aqua regia. Had we had chloroauric acid, as I'll show you in a minute, it doesn't work. And so had we made the catalyst with chloroauric acid, it wouldn't have worked. So it was lucky we had the wrong material to start with. So in 2007, Peter Johnson came into my office, who saw the picture of that, and he said that they'd bought the rights to this early work, and now they really wanted to commercialize it. The problem is that the early work used 2% gold, and this would bankrupt you, basically. And he said he wanted a method that used an aqueous solvent, not aqua regia, and he wanted to use 0.1% gold. And so he made the real breakthrough in this, and that is gold is a soft center, chlorine is a hard ligand. Gold, chlorine bonds are weak. And so if you make a gold catalyst with chlorine associated with it, it will form nanoparticles very rapidly. And you don't want that in this reaction. And so sulfur is a soft ligand. So a gold-sulfur bond would be ideal for this. And so using a gold thiosulfate catalyst with 0.1% gold, this is basically the commercial data. The blue line is the pilot plant data. And so the pilot plant is it's basically a single tube of 3 meters with 50 millimeter radius, 2 kilograms of catalyst. And then the full plant reactor, here you've got 790 of these tubes. And Pete made this catalyst by hand. He made 1.6 tons of catalyst in 2 kilogram batches and made sure it was sent safely to China to do this because he wanted it to work. And you can see the red line is the commercial data here, the full plant. And so, yeah, it's been rolled out. And if you want the full story of this, it's in this Jack's paper. So everything is in that. And so what was the active species in this catalyst? So the active species is fully dispersed gold cations. So this is the gold aqua regia catalyst, and these little dots on here are the gold cations. Thiosulfate, exactly the same. And when you do the in situ XAS experiments, you've just got gold chlorine bonds. This is the foil standard. But if you try and make the catalyst using chlororic acid with water as solvent, you just make huge nanoparticles, they're not really nanoparticles, huge agglomerates of gold, and the catalyst is totally inactive. And so it would have been bad if we'd done that. And if you then do the in situ experiment and you look at the white line height, which gives you an idea of whether it's gold 3 or gold 1, at the initial part, the catalyst is gold 1. It rapidly becomes gold 3 and then becomes back towards gold 1. And the activity dips initially and then increases. And you've got a direct correlation between productivity and the white line height. And so the more gold 1 you've got, the more active the catalyst. So if you make a catalyst with lots of gold 1 in it, it's the best catalyst that you can make. So the summary of this first part, which is something old, okay, this is a something old part, because it was pretty old at this point, but it is fully commercialized, which is nice as an academic to have something fully commercialized. And so the activity of the catalyst is highly dependent on how you make it. You can really make a bad gold catalyst very easily, okay? It's a little bit more difficult to make a good one, but it's easy to do. Aqua regias, you can make an active catalyst. The thing with aqua regia catalyst is it makes strong acid sites on the carbon, and so after many months you start growing acetylene polymers, and that's the problem with the catalyst, and so it deactivates. So you want something that doesn't have those strong. So thiosulfate is preferred as a first generation catalyst, and the gold sulfur bond is actually retained during use. We've done in situ XAS experiments, and we've looked at the chlorine edge and the sulfur edge, and one gold sulfur bond is retained during the active use. And as was mentioned right at the beginning, the gold catalyst is fully commercialized, and the Minamata Convention, which bans the use of mercury, has been put into international law in 2017. So I think although it's a nice example, because I'll say it's because it's mine, of where sort of fundamental science leads to a commercialized process that then changes international law. There aren't that many examples of that. And I was pleased to be involved in it. So there's something new, because this is not published. Okay, so I'll share something with you today which we've not published. But what could be another generation of this type of catalyst? And this is where we're using gold salts, stabilizing gold to make these highly dispersed catalysts. And the team now is getting bigger, I'm not going to read out all their names, but there's a very active collaboration with Johnson Matthey. Here Peter is still involved, although Peter retired from Johnson Matthey last year, and now he's a part of the Cardiff team because we've made him an honorary professor. So he now moves on to that team at this point. So, synthesis of new gold compounds. And these are really easy to make. And we got interested, we thought, oh, sulfur's fun, but what about using nitrogen? Or what about using phosphorus? Well, we haven't really got into phosphorus, but I'll tell you about nitrogen. So this molecule here, 2-methyl, so it's N-methyl-2-pyrrolidone. You can easily buy this, very standard. And you can make a very simple salt with this, and here's a picture of these lovely gold-coloured crystals that you can make with it. And it's basically, you just put chlororic acid into deionized water, you add 2 equivalents of NMP, it forms 2 phases because they don't mix. The aqueous phase, you pour it away, it's clear. Basically, the NMP phase contains these lovely crystals. And then you just dry it, and you get these crystals. And then you make the catalyst very easily by dissolving this in acetone. It has to be dry acetones. It can tolerate a little bit of water, but not a lot. And then you just add that onto the catalyst, and you could have this as a powder or extrudates, and then you dry it. And that's simple. You could all do this. You could all make these crystals. It's very easy to do. Even I can do it. So that's saying something for somebody who used to be an experimental scientist. I'm now an office-bound scientist, I would say. And because they're beautiful crystals, you can do the crystal structure. And so here's the crystal structure of this. And basically, there's 2 NMPs associated with the gold chloride, and one of the NMPs is basically protonated. And so it's a salt. You've got AuCl4 minus, and one of the NMPs is +1. And so it's a simple salt. And so do they work as catalysts? Yeah, works very well. So this is a 1% loading, because we tend to, for experimental users, use a 1% loading, because then you can characterize things. If you try and do microscopy on something with 0.1%, it becomes much more difficult. So we do it with 1% catalyst. And you can see with the powder, under our experimental conditions, and these, this is going on for 600 minutes, the NMP catalyst is better than the gold thiosulfate catalyst. Now that's interesting. This is a gold chloride catalyst stabilized by NMP, which over a period of time is still much more stable. So we thought, oh, this is really, really good. So let's make it on extrudates, which is where you would want the commercial catalyst at 0.1% gold, which is now, so the sort of reddish line here is the gold thiosulfate, the commercial, which would be the commercial catalyst. And you can see the NMP is tracking it, and then it's losing activity a little bit down here. So the extrudates, you're putting the gold just on the exterior surface of the carbon extrudate. And so this is a real test of this. So the NMP in a powder catalyst looks as though it's going to be a lot better, but it's just the same. The interesting thing, though, is they work a lot better at lower temperature, and that's quite an important thing. And so, does it matter how you add the NMP? Because the NMP is just helping there stabilize it. So you put the NMP on. So here's the gold catalyst with no NMP, the red line. If you put the NMP on the carbon and then add the gold, well, that's making no difference. If you have the gold on carbon and then add the NMP, it's worse. You actually have to form the complex, the NMP salt, before you add it to the carbon. And then if you look at the analysis, then you've got gold cations fully dispersed. You're not making any nanoparticles. And this is the thiosulfate catalyst, so it's identical to that. Now you can play games with this, because change the ring structure. So, and I'm only going to show you a few of the games that we play with it, okay? Because there's a lot of different structures that you can now start thinking of, and you can start thinking of other atoms that you can put into this. And so here's NMP, but as you grow the ring size, or you could leave the methyl group off. And so all of these you can make salts with. And you make these beautiful crystals, and then you can make the catalyst, and you can get the crystal structures. But as the ring size goes up, so the distance between the gold and the nitrogen is getting bigger. It's getting a greater distance. So the stabilizing effect of this material, this salt, is not as good, possibly. Oops. And with these, you make all gold cations. They fully disperse the gold, so they stabilize it very nicely. And when you look at the activity, though, of these, it's the NMP which is the best of these. The others are much lower activity. So the activity is highest for the NMP. There's a lot of data on this slide. I was trying to avoid putting lots of data on slides. And basically, if you've got the gold on carbon, and this is looking at 160 degrees, 180 degrees, and 200, so there's a lot on here. Basically, the take-home message from this is, as you increase the ring size, the catalysts lose activity, but they're more stable. And stability in the catalyst is important. So what we've been trying to think about now is how can we combine those two things? How can we get activity and stability in the same way? So this is work in progress. And sort of the summary here is that you can make these new compounds. And people hadn't really thought about this before, that you can actually make these very nice salts and use them as precursors for catalysts. And that the stability, clearly the NMP is still having its influence, even though this has been reacted at 200 degrees for several hours with the presence of HCl. So you can really form these strong bonds with the surface. And that we've got this reverse trend here. Stability is getting better as you go bigger, but the activity is going down. And it's a case of how can we get those to be coming together. So the next thing I want to step onto now is gold-palladium catalysts, something that I've been interested in for many years, as was pointed out earlier. And again, the team is getting bigger. So, the point here is not one person can solve these problems, and the amount of years that go into solving any one of these is immense. And we can have work that's been going on maybe for 10 years, and it's not, the key parts of it have not been published. There's always things that you can publish in a study, but you can always keep the key thing that you think is really important so you fully understand it before you publish it. I think that's important. So we have a big team working on this, and this goes back to the fact that if you have a gold catalyst for a very simple reaction, which is benzyl alcohol oxidation to benzaldehyde, really simple, very simple reaction. Gold by itself is not very good, palladium by itself is not very good, but the gold-palladium alloy is exceptionally good for this reaction. And so at this point, we published a paper in 2006 in Science, and a lot of people followed this, and they tried to explain what this was. It's referred to as synergy. Why was it a better catalyst? And we thought about that. Now, there's something borrowed. Is a really nice piece of work by Davis, and he showed that for a monometallic catalyst, the ODH and ORR reactions are basically sort of going on together, and that the gold catalyst, he was doing gold for a glycerol oxidation, and that the ORR reaction is crucial here, and the oxygen is playing it's not directly participating. It's forming the OH anions, and it's the OH anions that are actually the active species for dehydrogenating the alcohol. And so this is, the two processes. And so this is a very nice paper. And it also, a lot of people thought about it at the time. So what we were interested in is, what about if you have a bimetallic catalyst? Now maybe one of the metals would be doing the ORR, and one of the metals would be doing the ODH reaction. So can we improve things? And this is what's going on when we have these alloy catalysts. And so we thought, well, let's take a simple reaction to study. And so we chose HMF oxidation. It's a 6-electron process going through to this FADCA. And the reason we chose this is because FADCA is of commercial interest. Knowing what we know later on, I wouldn't start here. You want to choose the simplest reaction you can think of, not something that's really complicated, because the products that you'll make are going to be really quite difficult to analyze, etc., etc., etc. But we thought it's a really important reaction, lots of literature working on it, so it would be good. So we went into this. And catalyst preparation for this is really simple. It's a solar mobilization process, and we could all go out and make these catalysts. It's very, very simple. Basically, you simply take chloroauric acid. If you want to make a gold catalyst with polyvinyl alcohol, you dissolve them in water. You add a reducing agent. Other reducing agents are available, and this is NAB. This is sodium borohydride. Instantaneously, you form a gold sol. We then impregnate that onto carbon support. We use carbon support that's XR72. It's used in fuel cell applications, highly conducting, very important for this application. And when you make this, you get a reasonably tight nanoparticle distribution, somewhere around 3 nanometers. And then you could have gold palladium together, and you make a homogeneous alloy. And so we made a set of materials. This is a cartoon of them, basically, where you have a gold catalyst, a palladium catalyst. And then you can have a physical mixture of the two, where you put 50% of the gold in and 50% of the palladium, and just stir them in the reaction medium. And the other is you can make the alloy by having the gold and palladium solutions together in the same beaker. Or you can make a Janus particle, where you've got a small amount of, say, gold on one face of the palladium. And this is where you reduce the solutions separately, different beakers, mix them together, and then add the carbon. Basically, palladium loves gold. I love gold, but palladium loves gold more, it appears. And basically, the gold goes straight to the palladium. It's very difficult to make, and we've not managed it, to have a carbon support with a gold nanoparticle and a palladium nanoparticle separately to it. If any of you have got bright ideas of how to do that, please come and talk to me, because I really want that material. But we've not been able to make it. Many people have said they can do it. Nobody has actually, when they've tried to do it, been able to do it. So there's a challenge. If you can do it, get you 6 bottles of champagne. No. Although you have to come to Cardiff to get them. So these are the catalysts. And this is the microscopy of them, okay? So they've all got very similar particle size distributions, but this is the Janus particle here, where you've got this palladium here, and you've got this gold here. And this is the alloy. And if you look at these for catalysis, then we're looking at HMF conversion to start with here. So this is conversion, not to the product, just the conversion, the disappearance of this. And palladium is really bad for this reaction. Gold is okay. And if you have the alloy is more active than the addition of this and this. But the physical mixture is better still, and the Janus particle is better still. So the alloy wasn't the best. back in 2006. We missed a trick, and it wasn't until 2015 that we got these results. And my PhD student brought this to me, and I said, no, go and reproduce. No. So after he'd done it 6 times, I had to admit, okay, maybe the physical mixture is, putting them together. And you have to think, why is that? And if you look at the products being formed, then it really is significant, because the FADCA is 10 times higher than if you just have the gold there. It's a really significant effect on the final product. So we called this, there's a new effect, we called it CORE, Cooperative Redox Enhancement. It took us longer to come up with a name for this than to come up with the explanation for it. And we spent a long time coming up with a name. So we were quite happy with CORE. So if you've got better names for it, I don't want to know. And it's ubiquitous, so it works with diols, polyols, primary alcohols, secondary alcohols, aldehydes. It works, you see this effect, that the physical mixture or the Janus particle has much higher activity than the alloy. And so what's going on here? Well, basically, the palladium is doing the ORR reaction, and it's providing the hydroxyls that are doing the ODH reaction on the gold. So you're basically coupling these two together. So why is the alloy worse? Well, it's you're compromising the ability of palladium to cycle between palladium 2+ and palladium 0. And that causes the reaction to be less active. And so alloying gold with palladium inhibits that. And when you have a physical mixture, you don't have that. And so, this basically, and because this now is a model that you could test with an electrochemical way, you can do this with a cell, and you can get exactly the same results. And you can plot the two together and show that they map onto each other. So it's a nice reaction. So, and it doesn't just work with gold and palladium, by the way. It works with lots of combinations. It's basically just another realization of the electrochemical series, basically. So if you can form metal nanoparticles of various elements, it will work. So basically, the core effects are realized through this spatial separation of the metals. And there's the spatial separation is important. You've got the charge transfer, so you've got the electrons being transferred, but you've also got the OH in solution. So it's an important part. More recently, we've started to look at non-aqueous systems where you can't be coupling it with OH. And so if you have two reactions that you can couple in this way, which a lot of biological systems work by coupling reactions together, you can get this type of chemistry. So this opens up a lot of opportunities. So let's go on to mention the direct synthesis of hydrogen peroxide. And this is something that's just dear to my heart, I suppose. I've worked on this for over 20 years. And it's a very simple reaction. Basically, you're going to take hydrogen and oxygen, not in the explosive region, and react them together to hydrogenate the oxygen. But of course, you can hydrogenate that to make water. And of course, you can combust and decompose. These are both explosive reactions, and you don't want this. So, having spent 20 years on this, we can get catalysts that just make hydrogen peroxide. And so the site for this reaction is different for the site for this reaction. So you can decouple these two. And these need big nanoparticles now. This is a 40 nanometer gold palladium nanoparticle. And because of the way we make it, it's palladium rich on the surface. So the green here is palladium, and the gold palladium is in the core here. So it's around 40 nanometers supported on titanium. It's an exceptionally good catalyst for this reaction. But we've got one problem. We can make this high 100% selectivity, and we can do it with very high initial rates. We just can't make a solution in water that's concentrated enough for us to be able to distill it and make concentrated hydrogen peroxide. So we gave up with that. Well, we haven't, we're still going to try and do it. But the better way is to use hydrogen peroxide in situ as it's produced. So I want to give you some examples of this. I'll try and go through them quickly. Again, the project teams get bigger, they actually get more geographically spread, so you've got a lot of people working on this. But I'll point out that Kai Bowden was in BASF, and we were working with him on this at the time, and he was very valuable to us inside. And so basically, I'm going to couple an enzyme now with a chemocatalyst. And the enzyme is an unsaturated peroxygenase. And these things have only been around for the last 20 years or so. And what they do is very neatly take one oxygen atom of hydrogen peroxide and insert it into a CH bond. And so this is a really difficult reaction to do by a chemocatalyst, but enzymes do it really, really well. And they luckily use hydrogen peroxide. So let's use our catalyst that can make hydrogen peroxide in situ and put it with this enzyme. So that's the aim of what we're trying to do here. So very simply, we have our chemocatalyst here, which is a big nanoparticle supported on titania, and here's the enzyme. And we're going to make hydrogen peroxide, the enzyme's going to take it, and it's going to take cyclohexane into cyclohexane. Very simple reaction, okay? We learnt our lesson. Do something simple, don't try anything complicated. The problem is you've got a conditions gap. Because you want to make hydrogen peroxide, you use high pressures, you use low temperatures, high stirring speed, and enzymes don't like any of those. They want atmospheric pressure, ambient temperature, and they like to be shaken, not stirred. The opposite of James Bond, if you ever watch the films, okay? And they want to be buffered. They want to be pH 7. So can we make it work? Well, I wouldn't be telling you if it didn't work. We'd probably publish it somewhere, say, don't do it. So the classic way of coupling the enzyme is to use glucose oxidase as a way of making hydrogen peroxide, and this is classic. So this enzyme will make hydrogen peroxide, PADA1 will take it. So this is the classic way with a shaken reaction. Now what we've done is stirred that, and you see the enzyme doesn't like being stirred, but it's still okay. It's not so bad, okay? This is how much we're making a product. And then we add our catalyst in just to see if it kills the whole thing, and it doesn't. So that's okay. So we were quite happy with that. And then if you put the system together, now you have the chemocatalyst together with the enzyme, it works really well. And if you only have the enzyme, you don't get any product. And if you only have the chemocatalyst, you don't get any product. You have to have them both together to make this work. And what's more is it's better than the glucose oxidase way. The problem with glucose oxidase is it makes a byproduct acid. And this acid denatures the enzyme. And so glucose oxidase to start with, they're the black dots. Looks okay, but then after a few hours, it stops working. Whereas the in situ way of making hydrogen peroxide doesn't have that effect. And you can do this for hundreds of hours, and you can get several 100,000 turnovers of the product. So it's really, it works, and it works very well. And this was Kai Bowden who was helping us to get to this point. And what's more, you can get more complicated substrates, and here's a few of them. And what it means is if you basically retain, if you've got something which has a chirality, so you can have this, if you oxidize this, you can have the two chiral enantiomers. And when you make it, you retain the EE that the enzyme would give you, the enantiomeric excess of 98%. So you get all the good things of the enzyme, but you now get the in situ effect. It works very well. And so you can do this simply by having the enzyme, stirring it with a little flea here, with the hydrogen and oxygen being bubbled through it. Simple, works. So you can imagine doing this in a big vat, basically. Making sure you don't have much hydrogen there. That's the important thing, okay? So it works, so you can put an enzyme with it. The next example, a bit more complicated, this one. This is amoximation, and this is now a reaction which is taking off in China, and the project team isn't as big on this one, I must admit. But we were approached by Ube, Japanese company, to work on this. And basically, this is a process that's going to use ammonia at 80 degrees. And hydrogen peroxide will just decompose in basic conditions. So I said, I don't want to take your money. It won't work. And they'd contacted the British Embassy in Tokyo and set up. So we had a whole load of politicians sitting with us when they were explaining what to do this. And I had to say, no, you're going to waste your money. It's a shame, but you know, the thing is, if you think it's not going to work, it's best to say that at the outset, rather than saying, oh, I'll take your money and then it doesn't work. No, that doesn't go down so well. So, and they insisted that we did it. And I'm glad they did, because it does work really quite well, and I'll show you in a minute. So basically, the way in which you want to make this molecule here, and to do this, you make this oxime. And the classic way industrially is you take cyclohexanone and you react it with a concentrated sulfuric acid and ammonia. It's a hideous reaction. And you have a byproduct of ammonium sulfate. And historically, I'm going to say something terrible about industry now. Historically, I'm sure BASF never did this because you've got the Rhine and you wouldn't be allowed to do this, but ICI was on the edge of the North Sea, and so they put 400,000 tons of ammonium sulfate into the River Tees every year because it was almost worthless. So you're shaking your head, it's bad, okay? But you can't sell ICI shares because the company went bankrupt. Maybe because they kept no, probably not. I think it was bad management, actually. So the alternative, and the latest alternative, is you take ammonia with hydrogen peroxide and you form this very reactive intermediate, which you then react with TS1, and you get to this oxime. And this is the Sumitomo process using TS1. And so, can you use in situ hydrogen peroxide to do this? And the answer is, yeah, but again, you've got this massive conditions gap, because you really want to have subambient temperatures, acidic reaction conditions, and here you're going to be really basic at high temperatures. And so I was really skeptical we could make this work. But it works, and it works extremely well. Again, there's a lot of data on here. I just want to show that the various things here. This is the conversion for the first use, the first hour, the second hour, third hour. So the conversion's going up. The selectivity is pretty good as long as there's still substrate there. As soon as you start to convert a lot of the substrate, the selectivity starts to go down. And so you only want to do this at a partial conversion, not a whole conversion. So you can imagine having a couple of reactors in series to do this, where you do partial conversion and then a bit more conversion. And you can use lots of different substrates for this. So there's cyclohexanone, and then you can change the ring structure. And so it's sort of ubiquitous reaction for different ketones. Gold is crucial for this. Come back to my central theme of gold. Gold is crucial for this. If you have a catalyst which is just gold, so this is palladium content for this gold palladium alloy that you're going to make, the gold-rich formulations are the best for this in terms of giving you the selectivities that you're looking for. And any other element that you try and alloy with palladium doesn't work. So gold is the effective one for this. And if you look at this in terms of lifetime, whether you do it in the batch reactor and you recover the catalyst and use it time and time again, or you use a flow reactor, I mean, the data looks as though it's going up and down, but in terms of what we were looking for, this is quite stable over a period of 250 hours in this sort of flow reactor. And when you look at the used catalyst, it's very similar in terms of morphology. You don't lose any gold, you don't lose any palladium. So it's a very, very stable catalyst. And this slide is just to show you that if you think about the economics of this process, then the commercial Sumitomo process, the cost here is the cost of the materials. And then what you've got is the cost of the ammonia, which is much the same for all of them. And then you've got the cost of the hydrogen or hydrogen peroxide. And so with the sum of homo processes here, if it's with the problem with the in situ one, we're using a gold palladium catalyst, as you pointed out very eloquently. Gold's not cheap, and those palladium. So the catalyst has to last, and it must last. If it lasts for 2.3 years, then you've got a real commercial advantage for this. So we published this, and well, we were allowed to publish it. UBE lost interest in this. They lost interest in it because they could sell their ammonium sulfate at a premium because it was white, and farmers liked white ammonium sulfate. Typically it can be yellow. They won't pay much money for yellow ammonium sulfate, but white ammonium sulfate. So it shows you the sort of vagaries of commercial world. And so they offered us the technology back, and so we then effectively published it. And the day after the publication came out, we had 3 companies phone us up and say, we want this. So this is a very, really interesting area to be in at the present time. And this won the RSC Horizon Prize this year. And as I say, it's ready for scale up, and actually it's what we're discussing with a number of commercial things at the moment. And the last very quick topic, I hope I've still got time to do this, because I'm trying to show you the application of these across from being something that is fundamental science and how you can apply it. And so this is going to be water disinfection. Now, water disinfection typically uses chlorination, and chlorination leads to byproducts, and they can be toxic. But it works, and it's worked well for 100 years. Now, the water companies are the most conservative companies I have ever come across, and rightly so, because they deliver something into everybody's houses that if it goes wrong, it can have disastrous consequences. But chlorination is not the answer in the long run. If we're going to a zero, net zero economy, then chlorine, the making of chlorine, it's environmentally quite damaging, and uses a lot of electrons, and we want those electrons for other things, not making chlorine. So this is a team that involves a number of people in a number of areas, a number of countries, and this is where we typically use our in situ hydrogen peroxide to take water, which if you grow what's in it in an agar gel, this is what it looks like. But you put it through our reactor. This is a little reactor here, and what we're doing is it's basically doing 1 ml a minute. So we're not going to disinfect a lot of water using this, okay? But it really takes it down. And so we're starting with 10 to the 7 coliform units per milliliter. This is disgusting. This is worse than sewage. This is really nasty. If this was pathogenic E. coli, you'd be in serious trouble. And we basically knock that out. We do 7 log removal, so that's 9. There's 6 nines behind that. So that's quite impressive. And basically, again, you need to have the hydrogen and oxygen together over this. We've now scaled this up to basically 1 meter cubed per minute. So it's scaling up, and it's going nicely. But I suspect we'll get this into application somewhere in water-starved areas rather than Western Europe or America, where the water utilities will not go down this pathway just yet. But places in Asia could be really interested in this as a possibility. So but why does it work? And basically, again, it's this gold-palladium alloy that's crucial. So gold by itself, or palladium by itself, the red bars is how effective it is in knocking out these pathogens. And so you can see gold by itself, there's a bit of an effect, and palladium by itself, there's a bit of an effect, but it's the hydrogen peroxide that's being made in solution that appears to be the key thing that's going on here. Well, not necessarily, sorry. Why is gold palladium better than palladium? And palladium is making quite a bit of hydrogen peroxide here. And it's because the radicals that form hydrogen peroxide in palladium stay on the surface. They do not go into solution. So there's some very advanced EPR work behind this, basically this slide here. But when you put gold in it, those radicals go into solution. And you make a really very concentrated radical flux. And that causes cell damage and leads to the death of the pathogens. So this works on viruses, it works on a whole range of pathogens. And we're now showing it can also do chemical pollutants. So we're working, this is something which I think is, it's work in progress. There's very little, we publish very little on this. But it's something that we're very interested in. So you can use in situ hydrogen peroxide to do this, basically this water disinfection. We can remove chlorine. And in fact, it's 10 to the 7 times better than chlorination when you compare it in the same time scales. So this really is quite something that's potentially revolutionary. And we won the Ofwat challenge. That meant they gave us effectively £500,000. I'm underestimating the amount we won, to scale it up, to go to the next stage. And what we're aiming to do is to go into the next stage of this competition and get several million to try and take it to the next stage, because a metre cube per minute is still not very good. If you want to do a city, you've got to do 10 to the 8 metre cube per minute. So I've got to scale up by a factor of 10 to the 8. It's a bit daunting at the present time. But never give in. Never give up. It's possible. So with that, I'll give you my overall reflections at this point. And that is that however you make a catalyst, the way you make it is really important. And you've got to focus on that. There's a lot of work done here at the Fritz and in the universities where they emphasize that, the way in which you can make things. And the importance of the model systems and how you can understand things from model systems. Now, I've not done that. I've been making materials and using them, doing things. But underlying what I've been telling you about is all the model work that's gone on before this, and that's important. Active sites can vary with the reaction that's being catalyzed, and that's, I think, again, it's an obvious statement, but it's nice to show it occasionally. This new core effect, I think, has got a lot of potential that can be used by the community at large. And this in situ hydrogen peroxide, I think, can be combined with lots of things. Anything that uses hydrogen peroxide, this in situ approach, and of course it can be used in where you want it. You don't have to make hydrogen peroxide and send it by tanker somewhere in a concentrated form and then dilute it. You can make it at the place you want to use it. And so for distributed manufacture, it's the best way to go. And so this was where a lot of this work went on. This is the grade 1 listed building, the main building of Cardiff University. On an unusual sunny day, I think they had to wait 3 years before they took that picture. This is where the president of our university sits, the president here. When they found out that we were doing things with hydrogen and oxygen just around here, they weren't quite so happy, and they were quite easy to convince that we should have a new building. So here we have our new building. My office is here. We moved in about 18 months ago. Like all new buildings, nothing worked to start with. It took us 18 months to get everything to work, so I don't recommend you have a new building. Oh, you're having a new building, are you? History tells me, say no. On the other hand, it's lovely. Once it's finished and you've solved all the problems, it's really okay. And with that, I want to say thank you very much again for this award. It's a great honour to have been given this. It was a great honour to meet Gerhard Ertl today and have a lovely conversation with him. And to remember the first time that we met. And that goes back a long way. So thank you all. Thank you. Thank you.
Thank you very much, Graham, for this wonderful lecture. Maybe you want to stay here because we have a few things for you. First of all, I think it's very nice to have this slide there with the mention to what represents, I think, very nicely your research, catalysis, and then you have fun with catalysis. So our joint Max-Planck Cardiff Fundamental Catalysis Center. We are looking forward for many years of collaboration with you. We have Gerhard Ertl, who has been listening to your lecture, and I would like to transfer now the word to him, and I'm sure he wants to also congratulate you personally.
Can you understand me? Can you understand me?
Yes.
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 Thank you very much. I'm very much honored by the fact that this lecture, which was established many years ago, it is associated with my name, can still be continued. I'm very grateful to the organizers, in particular the BASF and its representative who enables this lecture going on. Thank you very much. I was very much impressed by your lecture, Graham. We met, as you mentioned, many years ago, and it's very amazing to see what you did all over all the years and how complicated it can really be. I wish you all the best for the future, and I thank you again very much for this excellent, exciting lecture. Thank you.
I would like to call now to the stage from BASF, Dr. Detlef Kratz, who is going to be giving with me the award. And I also wanted to thank Professor Blumenthal also for a beautiful introduction and our wonderful Laudatio. So thank you, both of you, for being here and doing this every year.
I hope you understood it.
So, Graham,
thank you.
congratulations.
Thank you. Oh,
Something to read.
oh, perfect. I like reading.
Good.
Is it a crime novel?
No.
You know. Oh.
I'm not sure how you are going to transfer this to
No.
Cardiff, but
No, I think
so we
not.
can send them to you.
Yeah, okay, thank you. Oh.
Picture.
Yes. Oh, yeah. Oh, yes. Yeah. Thank you very much. Cheers.
These lifetime works.
Oh, excellent. Hope I'm still alive.
So now, after this wonderful lecture, we are not going to have any questions, but we are going to have a reception. So we are welcoming everybody to stay at the entrance of the Harnach House. We are going to have a reception. I'm sure that you are going to get to talk to Graham and enjoy listening to his excitement, life, and science accomplishments. And thank you, everybody, for being here, and hope to see you in a bit.